Building a large-scale chemical manufacturing facility involves managing hundreds of moving parts, pressure vessels, kilometers of piping, and environmental controls, all while maintaining continuous production output. This isometric blueprint shows the dense infrastructure required to run two distinct manufacturing profiles simultaneously: high-heat solvent-based processes and moderate-heat aqueous systems. These tracks operate with completely different thermodynamic requirements. Housing them under a single roof means resolving these inherent conflicts before construction even begins. This diagram illustrates those divided targets. The plant must produce industrial alkyd resins on the solvent-based track, while simultaneously manufacturing water-based emulsions on the opposite track. When civil, mechanical, and chemical scopes are divided among disjointed contractors, misalignment is common. Equipment tolerances may not match, utilities overlap inefficiently, and safety standards fragment. Fossil Wood Engineering Services and Contracting addresses this by designing the entire facility through a single, unified methodology. Achieving operational efficiency across dual chemical tracks requires a master-planned framework, where every pipe and reactor is accounted for by one accountable source. This EPC methodology centralizes responsibility across three pillars. First, comprehensive engineering covers conceptual modeling through detailed mechanical schematics. Next, procurement enforces strict vendor qualification and global supply chain management for specialized components. Finally, construction provides site management, leading directly to pre-commissioning and handover. This capability is grounded in strict ISO-certified quality and environmental standards, refined across more than 30 completed industrial projects since 2018. This 3D macro architecture model translates our methodology into physical space, revealing the dual-track facility. Notice the physical compartmentalization of high-temperature alkyd reactors and low-temperature emulsion vessels, isolating their safety requirements. Yet, they are governed by shared thermal infrastructure and one centralized control room. By wrapping civil, electrical, mechanical, and chemical engineering under one roof, the integrated EPC framework reduces the client's scope of work and limits operational risk. Track A is the high-temperature solvent-based alkyd resin line. These resins are engineered specifically for high-weathering applications, industrial coatings, and color gloss stability through advanced non-drying oil formulations. Manufacturing these resins relies on rigid thermodynamic management to control the chemical reaction. This thermal profile maps the polymerization process, starting here at Phase 1, where raw materials are pumped directly from storage into the reactor vessel. In Phase 2, the system initiates a rapid thermal ramp, forcing the environment up to a peak of 240 to 250 degrees Celsius. This leads to Phase 3, the critical reaction plateau. Catalyst and polyol are added here, and the system must maintain a temperature between 240 and 260 degrees to ensure proper polymerization. Phase 4 requires a sharp cooling cycle, dropping the internal temperature rapidly down to 200 degrees Celsius. During this cooling, the system uses azeotropic distillation to continuously control polymerization and strip water from the batch. Finally, in Phase 5, the resin passes through automated filtration and transfers into a dilution blender, where final solid content adjustments are made. Track A is a high-heat, high-pressure operation. It demands mechanical engineering robust enough to safely contain intense thermal stress and solvent vapors. Track B shifts to the water-based emulsion line, characterized by moderate temperatures and a requirement for chemical stability. This track produces pure acrylics for architectural paints, textile binders, packaging adhesives, and waterproofing aids. This flowchart details the automated processing loop, which prioritizes prolonged, stable emulsification over raw thermal energy. In Stage 1, emulsifiers, additives, and water are charged into the reactor and brought to a moderate 80 degrees Celsius. Stage 2 activates the monomers and catalysts, triggering an active polymerization cycle. The system maintains continuous, monomered processing for 2 to 3 hours. Finally, in Stage 3, the product cools to room temperature. Here, the system relies on automated microdosing of additives to hit exact pH, solid content, and viscosity targets. Securing emulsion stability means maintaining exact chemical dosing over precise, moderate heat intervals. It is a different engineering discipline compared to the thermal extremes of alkyd production. Designing a facility that does both means housing these two opposed operational profiles under one roof. This operational matrix highlights the divide. Track A handles volatile solvent and oil-based carriers, while Track B relies on water-based systems. The thermodynamic delta is significant. Alkyd polymerization peaks at 260 degrees Celsius, whereas emulsions operate at a moderate 80 degrees. Consequently, the two tracks require different environmental and safety protocols to manage everything from vapor emission to chemical handling. Running these opposing matrices side by side without compromising safety or efficiency requires a unified command structure that ties them together. The solution is a centralized SCADA infrastructure, supervisory control, and data acquisition. This architecture physically and digitally integrates the Alkyd and emulsion lines, letting operators manage both tracks from a single pane of glass. This enables intelligent energy optimization across different thermal profiles, reduces required floor manpower, and ensures unified safety standards across all zones. Integrated automation consolidates these contradictory chemical processes into a single, controllable manufacturing platform. Scaling these master-planned facilities to a global level demands a physical infrastructure capable of fabricating and deploying heavy industrial hardware across continents. This map outlines Fossil Wood's global footprint, anchored by their manufacturing headquarters in Chennai, India. From there, operations expand to Magdeburg, Germany, and Dubai. This presence allows them to build equipment in-house while integrating components from a certified worldwide vendor network. Operating dual tracks at 260 degrees and 80 degrees simultaneously requires both microscopic thermodynamic precision and macroscopic global execution, delivered through a single accountable partner.